Good morning, AP Calculus students. So for those you need to take the test next week, so here's another video. So this one is for the 2018, the free response for Calculus BC. So what I'm going to show you here today is some of the problems. So things that most likely is going to be tested. Well, it's not going to be the exact same thing, obviously, but it's going to be a similar problem like this for the free response for the Calculus BC test. And this year is a little bit special. It's a pandemic time, so instead of taking the test on sites at the school sites, so there's no multiple choice. It's only 45 minutes, and you guys can use your notes, everything. It's only probably like 5 to 6 problems, and there's something that's being cut off. There's no sequences in series. Probably there's no polar stuff. There's no parametric. But one thing that you need to watch out, they probably put in like optimizations problem, and also they'll probably raise up the regress of some of the problem that you guys have done previously, and we'll take a look at that. Okay, so once again, this one is for 2018. So the free response for 2018 calculus BC test from the College Board. Okay, so now we'll take a look at some of the problem here. So the first one, people enter a line for an escalator at the rate modeled by the functions r given by the piecewise functions. And as you can see that here from 0 to 300, well, this one, I think it's a second. Yeah, it is. And so we do have an equation 44 times t over 100 quantity to the power of 3 times the quantity of 1 minus t over 300 and the whole thing to the power of 7. And then the other one is after that, people entering the line, it's 0. So again, this one, it just shows the number of people enter a line for an escalator. So for t is greater than 300, so there's no more people entering the line. So r of t is measuring people per second, and t is measuring second. And as people get on the escalator, they exit the line at the constant rate of 0.7 person per second. And there are 20 people in the line at time t equals 0. So that's just given the condition here. So the initial condition that at time equals 0, there are 20 people in line already. And how many people enter the line for the escalator during the time interval from 0 to 300 seconds? So the number of people enter the line from 0 to 300. So basically this one, we just want to take the integral. So we basically take the integral from 0 to 300. Okay, so let's just set up the integral. So 0 to 300. And then we just put in that r of t. And then we want to find out what that is on the calculator. So in the calculator, so here's what you want to put in. Okay, so anytime that you use the calculator, make sure that the mole got to be in radians. So in case that anything that pops up with trig radian, so it's already in radian mole here. If that's not the case, then you want to switch that back to radian. And now let's go to the function. We can use that y equal. Okay, so let me just show that the keystroke here. So y equal, or you can go back to second and quit, and then y equal. So now we want to put in the equation. So the equation for this one, which is 44 times. So instead of using t, we're using x. So t over 100, so x over 100. And then to the power of 3. And then times 1 minus. Got to be careful the minus. We're using this sign as the minus, not the negative. So t over, I think it's over 300, right? So x over 300. And then the quantity to the power of 7. So making sure that this one got to be exactly the same equations. So we're going to use this one as the integrand. So we can integrate it from 0 to 300. Okay, so now And that's the equation here. So now you want to go back to the home screen. Okay, so let's just clear all this. So now you want to go to math and then integral. And the lower bound, we do have 0, starting at 0 second. And then it goes all the way up to 300 seconds. So now instead of putting the function for the integrand, we can just enter that y1. Okay, so let's just move that, the cursor, all the way to this blank. So now the way to find out y1, so you want to go to vars, y-vars, and then function y1. And then we're integrating it with respect to x, not t. There's no t here. So, and then press enter. So it's exactly 270 people. Okay, so 270 people. So basically, once you integrate it, so you can find out the exact value. Sometimes, so it depends on the evaluator, so it's a little bit picky. So make sure that you put in the unit people. Okay, so now let's see what the next question is. So for the next one is showing that during the time interval 0 to 300 seconds, and there are always people in line for the escalator, and how many people are in line at time t equals 300. Okay, so we're going to find out. Now for this one right here, so this one is showing that the number of people in line. Okay, so start at time t equals 300, so that means we need to put in the initial condition as well. So the initial condition, we are saying that, so for p of 300, so initial time, we do have 20 people waiting on the line already, so 20 plus, so the integral that we have from 0 to 300, r of t, the one that we found for the previous questions, and then minus, while people are getting out from the line right here, so 0.7, so that shows the rate, 0.7 times the time, so the end time here, it's what, 300 seconds, subtract. So try to do that on the calculator. We do have 20 plus 270 minus 0.7 times 300, so we do have 80 people. Again, that part you can do that on the calculator. It's pretty basic. Okay, so at time t equals 300, so we do have 80 people in line. And now for t is greater than 300 seconds, so what is the first time t that there are no people in line for the escalator? So now this one, the key word is that there are no people in line. So that means we need to find out the final amount. It's going to be 0. So the final amount is going to be 0. So we do have p of t. So again, this one is quite similar to part B, but we need to set the result equals 0. So 0 p of t equals 0. So that equals 20 plus 270, because that's what we found for part A, 270. And then minus 0.7 times t. So this one you can just solve it by hand, or you can just do it on the calculators. So you do it on the calculator, you'll get 414.2857, blah, blah, blah. It's an irrational number. Or you can just round it up to 414.286. Well, this one's supposed to be, yeah, that's right. So 414.286 seconds. And now for part D, so for zeros in between 0 to 300 seconds, so at what time t is the number of people in line, minimum, and to the nearest whole number. And then find the number of people in line at this time and justify the solution. So this one you need to think about the way to find the minimum. So it's about the optimization problem. So in order to find out that's the minimum, so we do know that t equals 0, and then t equals 300 seconds, and we need to set that p prime of t equals 0. Again, it's about the optimization problem. So what we need to do here, we take the derivative of p of t. So we end up with r of t. So using part 1 of FTC, minus 0.7, because that 0.7 times t. And then from here, we can find out that t equals 33.013 second. And also, we'll find out that t equals 166.574 second. Again, r of t, so instead of using that integral, we just put in this one. So this one would be considered y1 minus 0.7. Okay, it's for p prime of t. And then you want to set that equal to 0. So let me show you the way to find this out on the calculator. So now what we got here, it's r of t already for y1. So y equals, so that's r of t. So we go back to the home screen. Okay, clear all this. So we're using solve to find out the 0. So second, and see that catalog right here. Well, there are two ways you can do it. You can do it in this way, algebraically, or you can do it with the graph. So I'm going to show you both. Okay, so look for the word solve. So go to second catalog and then press 5, and then press the upper cursor again. So the word that you're looking for, it's solve. So we're almost getting there. Okay, right there. Okay, going too far. Okay, I need to go back down a little bit. We just passed by. So look for the word solve. So here we go. And then press vars, and then y vars, minus 0.7, and then comma, x, and then comma. So you need to do some kind of approximation guess, so you can put in any random number for this. So for the first t value, we do have 33, so let's put in any random value. So let's say it's 29. So the first x value, so t, which is what, 33.0132978 second. And then we use the exact same kind of operation. Okay, so this one can always copy it and then just change the value, and then change that to t equals 167. So you get that the other value. Okay? So once you do that on the calculator, you'll find out those two times. And then this one you want to just justify the solution. So at p equals 0 is 20. So you want to say that. And then p of 300 is 80. So p of a, so once you plug in the time back, and then you'll get 158.07014 people. Okay? Well, you'll get 3.803. You'll get about 3.8 people. Well, you want to round it up, so it's 4 people. So if you just plug in the time back to the p of t, so p of 33.013, so we get about 3.8 people, but you want to round it up. People cannot be decimals, so 4 people. And then the other time that I put in back there, so it's 166.574. Because one of those would be the min, the other one would be the max. So the other one is actually the max. It's 158.07. So round it up, so it's 158 people. Okay, so that means 4 people would be the minimum. And that's the time, so which occurs at 33.013 seconds. Okay, so that's the first calculator problem. And now let's look at another one. Okay, so here's number 2. So researchers on the boat are investigating plankton cells in the air, in the sea, at the depth of h meter, and the density of the plankton cell in million of cells per cubic meter. It's modeled by P of h. So it looks like it's an exponential decay function, 0.2 h squared times e to the power of negative 0.0025 h squared, and h is from 0 to 30. And it's modeled by f of h, for h is greater than or equal to 30. And the continuous function f is not explicitly given. So find out what p prime of 25 is using the correct unit, and interpret the meaning of p prime of 25 in the context of the problem. Okay, so this one, it's a little bit special. So it looks like there are a lot of things you need to set up here. Okay, we'll take a look at that. So thinking about that, the equation, okay? So it looks like the equation shows the rate of change. So it shows the rate of change. And also the rate of change can be modified by the unit. Okay, so think about this way. So let's say millions of cells over cubic meter. So times meter square times meter. So once you multiply by meter square and meter, guess what happened? The unit got canceled. The bottom unit, the 3-dimensional cubic meter, the volume unit with the 2-dimensional and 1-dimensional unit would get canceled. And then the only thing that you left here is just million of cells, which is the number of cells. Okay? But now this one you want to find out what p prime of 25 is. Okay, so basically we can use this model to determine the rate of change at 25. Okay, so basically for that one, we can just simply take the derivative. So once you take the derivative, okay, so let's just type in that function, and then you plug in 25. Okay, so let's just put in the function. So what we got here, y1 again, so it's 0.2 h squared, so 0.2 x squared, 0.2, again there's no h, so we're using x squared, times e to the power, so second, base e to the power of, so I need to go back and forth, so negative 0.0025 h squared. Negative 0.0025 x squared. It's got to be really careful with the way that you enter the functions, okay? The power and the exponent. Looks like I did something wrong here. Okay, let's start it over with this one. So again, 0.2x square. Forgot to bring down the cursor back down here. So, and then times second e to the power of negative 0.0025 x squared. Okay, making sure that is correct for the functions. Okay, 0.2 x squared e to the power of negative 0.0025 x squared. Okay, so now, and this one, it just shows y1. And now we want to find out exactly what the rate of change is at 25 second. Okay, so second, quit. And now we're going back to the home screen here. So now this time we're using the derivative, so math 8. So d over dx, we put in x for that blank. Again, instead of putting the function again, we're using vars, y vars, y1. And then for the x value, so this time we want to put in 25. And here's what you'll get. It's negative 1.179 millions of cubic cells per meter. So that shows the rate of change. Okay, so let's go back to that. Okay, so for the first one, if you just do it on the calculator, well, you still need to show a little bit work here. So even you just do all the whole thing in the calculator, so just show that p prime of 25. So that's about negative 1.17906. The thing is that it doesn't tell you to round it up, so just show the whole decimal here. So whatever that you have for the rest of the decimal number there, just put it in. And the unit is very important. So this shows that the millions of cell cubic meter per meter. Okay, so it's the same unit as this one here. Okay, so now let's take a look at that. The next one. Oh, you know what? We need to identify the meaning of the content. Okay, so what that means is showing this one. So this means that the depth of 25 meter, the density of the plankton is decreasing at the rate of 1.179064048 million of cell cubic meter per meter. So again, this one shows that the density of the plankton is decreasing at the rate of that amount. Okay. So now the next one. Consider a vertical column of water in the sea with the horizontal cross sections of the constant area, 3 square meter. A lot of things going on here. So let's underline the key phrase. So vertical column of water. And the cross section, which is what? It's horizontal cross sections of the constant area, 3 square meters. Okay. So to the nearest millions, so how many plankton cells are in this column of water between h equals 0 and h equals 30 meter? Okay, so this one got to be really careful about the unit. So again, what I mentioned about this one earlier, so the millions of cells per cubic meter, so that shows the rate of change, times meter square, which is the area, and then times meter. Meter, that's just the height, the change of the height. Okay, so back to the unit that we have. So it shows the rate of change. It shows this one here, which is the area, and then dh. So the way that we need to set up the integral for this is from 0 to 30. And then we want to put in all the information. So p of h times the area. So the area showing that's 3 square meter. And then times dh. So the change of the height. Okay? Or you can just say that's the indicator. Again, if you try to do that on the calculator, so this one will give you about 1,675.4. 14936. If you try to approximate it, so it's about 1,675 million cells. Okay, million cells. Okay, so that's a lot of cells there. Okay, so now let's see the next one for part C. See what that is. So this is the functions used such that from 0 to, okay, it's from 0 to u of h, and where f of h is right in the middle. And for h, it's greater than or equal to 30. And then the integral from 30 to infinity, u of h dh is 105. And the column of water in part B, it's K meter deep, and where K is greater than 30. Okay, so part B, we have to use this solution here. And write expression involving one or more integral. So that gives the number of plankton cells in million, and the entire column. Explain why the number of plankton cell in the column it's less than or equal to 2,000 million. Wow. So let's try to digest this one a little bit. There's so many information given here. So we do know that the integral from 30 to infinity for u of h, it's 105. And one thing that we notice, u of h is greater than f of h. Okay, so where k, it's the depth of the column of water. And where k, it's greater than 30. Okay, so first thing that you want to do, you want to write expression involving one or more integral. That gives the number of plankton cell in millions in the entire column. And then the second part of this, you want to explain why the number of plankton cell in the column it's less than or equal to 2,000 million. Okay, so now one thing that I can do. So let's start it with some kind of substitution here. So since we do know that the depth of the water it's greater than 30, so we can say that from 30 to K. Okay, and then u of h dh, so that equals 105. While k is going to be a certain number, it's all the way up to infinity, so it's k. So instead of using infinity, we're using constant k. Okay, so started with this one first, and then the next one we'll set up that the equation. Okay, so the equation with the inequality. Okay, so the second part of this, so let me just bring it down here. So for the million cells, so we can set up that integral from 0 to 30, and then p of h, okay, this one's 30, excuse me, times 3 times dh, and then plus, so what we just found, the one that's given, so from 30 to k, because that's more than 30, and then f of h times 3 times dh, so from 0 to 30, we found that amounts already, so a, so that's the previous solution. What we got is 1675. So this one is 1675 plus, well, this, the integral from 30 to k, f of h times 3 times dh. And one thing that we know, f of h is less than u of h, so this one you can set that it's less than or equal to 1675 plus integral from 30 to k, so u of h times 3 times dh. So this one is kind of like a comparison, or you can say that's kind of like using the limit of the squeeze theorem. And then the rest of this, you just want to verify it. Okay, so this one, it's less than or equal to, so just a continuation. 1675 plus integral of 30 to k. Instead of using k, we're using infinity because that's a given condition already. Okay, so from 30 to infinity. And then u of h times 3 times dh. Okay, so just like that. And then, so basically we can just, by plugging the number, so we can just set up the whole quantity. Oh, you know what? This one, actually, it's not 1,000. Excuse me. So the value of a that we find out earlier, so once you integrate it, it's actually Wait, hold on a second. Yeah, that's right. So A is 1,675. So once you combine this all together, so eventually you're going to end up with 1,990.415. Again, you don't want to round things off yet, so which is less than or equal to 2,000. Okay, so again, this quantity is already given, which is what? It's 105 times 3. Okay, so basically this one integrated, and then it's 105 times 3, and then combined it with 1,675, and then you get this number. So it's better for you to show one more step here. So instead of doing it all together with the calculator. Depends on the evaluator. It's very picky, you know, for some people because they really want to show all the work. They really want to show all the step, the process. So this one can say that's 1,675 plus 3 times 105, and then it's 1,999.4. Well, 1,990. Excuse me. 0.45, 0.415. So which is less than or equal to. It's almost getting close to 2,000. You take the limit. Okay, so that's what we got. And now let's see what else that we have for this problem here. So the last part of this questions. Okay, so the boat is moving on the surface of the sea. At time t is greater than or equal to 0, the position of the boat is x of t, y of t. So kind of like a parametric. And where x prime of t is 662 sine of 5t, and y prime of t is 880 times cosine of 6t. So time t is measured in hour, and x of t and y of t are measured in meter. So find the total distance. So basically this one kind of like finding the arc length. Okay, so let me just put in down here. Okay, so let's clear annotation. So what we can do for this one, so we can set up the distance, which is the arc length. So from 0 to 1, because that's the time interval. And then we do know that the general formula for the arc length would be square root of x prime of t, and then quantity square. It's kind of like a Pythagorean theorem. And then plus y prime of t, quantity square, and then dt. Because once we just integrate all the small segments, the distance together, so we get the total arc length. So basically just put it into the calculator. So for this one, you want to convert that to the equations, so the parametric. But according to, for this BC test, I don't think there's going to be like a parametric problem. But just in case, okay? So just in case. So you want to convert that to parametric, so you want to go to the mode. And then you guys see that under function right there. So you can always switch that to parametric. Again, making sure that it's in radian mode. Okay, so now you want to go to y equal. So for x prime of t, let's see what we got for x prime of t. So x prime of t, you can enter that 662 sine of 5t. So sine of 5t. And then for y1, so y1t, you can enter that y prime of t right there. So y prime of t, so we do have 880 cosine of 16. Okay, and then cosine 16. And then the rest of this, you want to go back to the home screen. Same thing like what we did earlier. So math. And then 9. Integral. From 0 to 1. And now got to be careful with that. The integrand here, we want to put in the square root first. So second x squared. And now this time, so you want to find out that the parametric. So parametric, you want to go to vars again. Y vars, but this time is parametric. So it's 1. But make sure that you need to raise up that to the second power. Square. Bring down the cursor back. And then plus. Again, vars. Y vars. But this time, parametric. So 2. Quantity square. And this one, indicator. DT. Press enter. So the way to set it up is quite easy, but the things that make sure that you know how to use the calculator for this. So eventually it's 757.4558623, and then just round it off. So 757.456 meters. Okay? So that's the last part of problem number 2. So for the calculus BC test, the free response, the first 2 problems, they're always considered calculator. And then the last 4 problems, they're going to be considered non-graphing calculator. So 45 minutes, I think they're going to cut off the last one. So there's no sequences in series. There's no Maclaurin. There's no Taylor. There's no Lagrange. Okay, so but the thing is that in case that they're going to give you like parametrics, so make sure that you know what to do. Okay, so now let's see what else that we have for the rest of this. So now the non-calculator section. So for the non-calculator section, so guess what? I'm going to cut off this one because the video is going to be too long. So the second video I'm going to put up there is going to be the non-calculator. Okay, so you see that later on today. Okay, so thank you for watching the first part of the Calculus BC. So the 2018